Welcome back. In this video, we're going to talk about data types in Go and how to declare variables in Go. So first, before we go into data types, I want to give a really quick crash course on bits, bytes, and binary numbers. If you already understand this material and concept, then you can skip ahead. But for those of you that don't, I'm going to try to go through it really quickly because knowing this will help you understand what I'm talking about when I talk about the different types of data types. So most of you probably never need to know this in coding or software engineering. But I actually personally do use it a lot at work. But anyway, let's go. So what's a bit? A bit is the smallest unit of data in a computer. It's either a 0 or 1. That's it, nothing else. 0 or 1. Simple enough. So a byte is 8 bits. That means that we have 2 to the 8 possible combinations or possible values that can be represented in a byte. That means the largest value we can have is 255. 0 to 255. That's 256 different numbers. So that's 1 byte. 1 byte being 8 bits. Okay, so a binary number is a number in base 2, and a decimal number is a number in base 10, which is the base system that me and you grew up with in school. So that's why we're really comfortable using base 10 numbers. But if hypothetically we did grow up doing binary in school, we would be all comfortable with binary, and decimal would be the odd one out here. So what I'm trying to get at is binary and decimal are the same. They work the same way, except that binary is base 2 and decimal is base 10. Binary is base 2 because there's only 2 possible values, 0 or 1. Decimal is base 10 because there's 10 possible values, 0 through 9. So here, this little subscript represents base 2, and this little subscript right here represents base 10. So this is a binary value right here, and this binary value right here represents the decimal value 4. So being that I do use binary numbers quite often, I can easily see that this is 4, but if you wanted to prove that this is actually 4, or show that it's 4, you would do this calculation, and I will walk you through it really quickly. So this is considered, so this is 4 bits right here. Remember, each bit is either 0 or 1. So there's 4 bits here. This bit to the right hand over here, usually called the LSB or least significant bit, is bit 0. This one is bit 1. This one is bit 2, and this one is bit 3. Just like indexing in an array, we start counting at 0. Like the joke programmers always start counting at 0. Anyway, so how do we calculate this? So I should have added the formula, but with variables and such, but I'll explain it. So you pretty much sum up these 4 bits here, and what you do is, this first calculation here is 0 times 2 to the power of 0. So this 0 represents the value of the bit right here, which is 0. This 2 right here represents the base. We are base 2 because we're in binary. And then 2 to the power of 0, because this is bit 0. So let me repeat that one more time. This 0 represents the value of this bit. This 2 represents the base. And this exponential represents the bit number. So that's for the 0th bit here. Now we do plus and we go to the next bit. This bit has a value of 0 here, so we do 0 times 2 to the power of 1 because it's base 2, and it's to the power of 1 because this is the first bit here. Remember, this is bit 0 and this is bit 1. Now we do plus 1 times 2 to the power of 2 because the bit here has a value of 1. So it's 1 times 2 to the power of 2 because it's base 2 here to the power of 2 because this is the second bit. Bit 0, bit 1, bit 2. Final calculation, plus 0 times 2 to the 3 because the value at this bit is 0 times 2 to the power of 3 because this 2 represents base 2 to the power of 3 because this is the third bit. This is bit 0, bit 1, bit 2, bit 3. This is considered the MSB or most significant bit in this case. And if you do this calculation and you add it all up, we get 0 plus 0 plus 4 plus 0, which is equal to 4. So this binary value here equals 4 base 10. So that's how you can do the conversion. It's very long when you think about it, just even for 4 bits. So most times you could just punch into a calculator, or if it's like this, you can easily see it if you actually use binary numbers for a while. Anyway, and I have this other example here of showing that 19 base 10 running through the same calculation above is equal to 19. Because I want to show you that binary and decimal it's the same concept, except that the base number is different. So we do the same calculation here. We do 9 times 10 to the power of 0, because the value here at the 0th place is 9. So you do 9 times 10 to the power of 0, because it's the 0th place and it's base 10. Now we do plus 1 times 10 to the 1, because the value here is 1, and it's 10 to the power of 1 because it's the 1's place here, 0, 1, and then it's base 10, so it's 10 to the power of 1 times 1, and you do the calculation again, so it's 9 times 1 plus 1 times 10, that gives you 19. Now, that's that. So that's how you go from binary to decimal. Okay. Now, unsigned versus signed. What does this mean? So if someone tells you that this integer is a signed integer, that means that there is a bit. So hypothetically speaking, let's say someone told you this value up here is signed. That means that there's a bit in here that represents if the number is positive or negative. Most of the time, it's the MSB or the most significant bit that is used as the signed bit. So depending on the computer architecture you're using, if the MSB or the signed bit is 0, then the number is positive. And if the signed bit is 1, then the value is negative. So that's what it means when someone says the value is signed, or a signed integer. Now, if someone says the value is unsigned, or it's an unsigned integer, that means the number is always going to be 0 or positive. Because since there's no signed bit, we can't tell if this binary number is positive or negative. So that's signed versus unsigned. Now, this is an example of a 32-bit integer. This is how it would be represented in register computers or whatever. Personally, I actually would have had 31 start here, and then 30, and 29, so on. Pretty much flipping this, but it doesn't really matter. Like I said, depending on your computer architecture that you're on, the Indianness would determine that layout. But that's irrelevant as of right now. So an integer, 32-bit integer, is signed, meaning that there is a bit that will let us know if the value is positive or negative. So, well, we can hypothetically say that this bit here at bit 0 would be the signed bit. So 0 means that this binary number is positive, and if there's a 1 here, that means you know this binary number is negative. And actually, this whole thing here represents 1, pretty much, because you do the whole calculation as I showed earlier, and flipping and changing this 31 here to 0 and then 0, 31. So flipping the order here, you would see that it would be 1 because all these are 0. But anyway, so what that means is that we have 32 bits in here, one of them being used as the sign. So that means we have 31 bits that are available for rearrangement and combinations. So that means we have 2 to 31 combinations, but which is 2,147,483,648 But since we do have the sign bit, that's kind of doubled because we can represent the negative values as well. So we can represent values from minus 2,147,483,648 to 2,147, no, 2,147,483,647. Um, so that's how many different values we can represent using a signed 32-bit integer. This is doubled here because you're representing the positive and negative values. So this statement's kind of incorrect here. And so this is the same situation for 16-bit integers and 64-bit integers. Obviously, a 16-bit integer wouldn't be able to represent as many numbers as large values, and obviously integer 64 would be able to represent much larger values. So those were just whole numbers, integers being whole numbers, and now we're going to quickly go over float, which is for decimal point numbers. So like I said earlier, depending on your computer architecture, your computer could represent the bit layout of a float differently than this diagram here, but I'm just going to use this for now. So hypothetically speaking, let's say our computer architecture is representing our float like this. Well, this binary float representation is equal to this in decimal, 0.15625. So if I wrote this in my code, this is how it'd be represented in the computer. So how do you read this? Well, the first bit is the sign bit for positive or negative value. These 8 exponent bits represents a signed integer from minus 128 to 127. You can trust me on this. Unless you don't trust me, you can do the calculation yourself. This is for like the whole number part of the decimal. And then we have 23 bits for the fraction. This represents the values after the decimal, the fractional part. And this equates to 32 bits in total. So with this information here, we can calculate the value by going through this formula. Negative 1 to the power sign, the sign being the sign bit, 0, 1, times 2 to the power of e minus 127. E being whatever signed integer is represented here. In this case, it's 124. You can punch this into a calculator or calculate yourself. This will be 124 in decimal. So, and then you do times 1 plus the summation here of 1 to the 23 of b subscript 23 minus I times 2 to the minus I. So now that we went through the formula here, we will run through the calculation. So the first part here, since the sign bit at bit 31 is equal to 0, we do negative 1 to the power of 0, which gives us 1. That's the first part here. And then the second part, we do 2 to the power of 124 minus 127, which gives us 2 to the power of negative 3. Because e here equals 124 because the 8-bit signed integer here is 124 in decimal. So that gives us 0.125. Now the third part here is a bit tedious because of this summation here. So I cut it short, mainly because most of it's just all zeros. So let's go through this. So the third part here is 1 plus summation, 1 to 23, b23 minus I to the minus 1, blah, blah, blah. So this is equal to 1 plus, and then this is the summation here in parentheses. Let me make this bigger really quick. Okay. So summation is from 1 to 23. So we start at 1. So b23 minus 1. That's b22. So if we look at bit 22, is the value 0. And actually, the first bit here in the fraction we don't use for reasons I'm not going to go into. So we can skip this one actually and go to the next iteration of this summation. So now we're at 2 in the summation. So b subscript 23 minus 2 is 21. So at bit 21 right here, we have this 1 here. So that's why we have 1 times 2 to the power of negative 2, because I is 2. Next, we're at 3 in the summation. So 23 minus 3 is 20. So at bit 20, we have a 0 here. So that's why we do 0 here times 2 to the power of minus 3, because I is 3, it's 2 to the minus 3 here. And blah, 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 you go all the way to the end here, the last one here, of 0 times 2 to the minus 23. And doing this, adding up the summation, and then the plus 1, we get 1 plus 0.25, which is equal to 1.25. So this third part here in the formula gives us 1.25. So the last thing we need to do is multiply all 3 parts together. So we have 1 times 0.125 times 1.25. Let me see, did I misspoke here? All right, let me say that again. So the final calculation is 1 times 0.125 times 1.25, which gives us 0.15625, which is equal to what we have up here. So that's how you would convert this float binary representation to a decimal value. And float 64 is similar, but is more accurate because we have more bits, so we can represent a more accurate fraction. And I believe in 64-bit floats, we actually have 11 exponent bits, and then whatever extra is put into the fraction, I believe. So that's that. Now, so I'm going to my data types file here. There's no real code that really executes or anything. So these are the basic types in Go that I'm just going to briefly talk about. You can see the full list of all the basic types in Go here, which we will look at as well. So we have unsigned int 8, uint 8, int 16, int 32, int 64, float 32, float 64, and rune. And on the left here, on the left side of the hyphen, is the actual syntax for the data type in Go. So on the right is the description, unsigned 8-bit integer, which is what I talked about in the slide, the 8-bit, the byte, which is 8 bits, unsigned. And I showed this as well, the signed 32-bit integer. This is the range of values that it can hold. See, if you can see the signed 64-bit, this huge number. Most of the time, this is usually probably enough for most cases, but you never know. And then flip 32, I showed you guys in the slide as well. And then this is float 64, which is a decimal point value, but you're using 64 bits to 32, so it's more accurate. And then rune is similar to 32 in 32, as in that it's a 32-bit value, but we use rune for Unicode, so like characters and stuff. So like if you wanted to print, the @ character in the email or something, you would use rune. And so this is probably, oh, I forgot, and there's string, which is simply just a string of text. But these are probably all we're going to need for the rest of these videos. But we can take a quick look at the other ones that I did not mention. And, and there's Boolean. Definitely going to use that probably. It's either 0, 1, or true or false. And the string, like I mentioned, these are the ones I showed in that file. So are these. Did not talk about this. There's byte, which is the same as uint8. Went over this in the slide. And then rune, like I mentioned, for Unicode. And then the 2 floats. And then we also have types for complex numbers, actually. And then here's a brief explanation of some of these. So int, usually 32 bits, blah, blah. Okay, cool. So if you want to look further, you can visit this. I'll have all the links and everything in the video description. So that's the basic data types in Go. Now we're going to talk about how we can declare variables in Go. So we have three ways that you can declare a variable in Go. The first way is this. Var for declaring means we're declaring a variable, and then the variable name, which I called my name, and I set that variable equal to the string of Kevin. So what this line here means is that we're declaring a variable called my name, initialized with a string value, this string value here. Another way we can declare a variable is we can declare a variable, but we don't initialize it with a value. So I don't say equals something. I just declare the variable. So here I write var for variable, and then the variable name, my age, and I specify that this variable is going to be an integer 32 data type. So this variable holds a 32-bit integer. Now, since I did not initialize this variable with a value, it's defaulted to the 0 value. And right here, I have a note. Variables declared without an initialized value are given their 0 value. So whenever you declare a variable and you don't initialize it, they're given a defaulted 0 value. So if it's 0 for numeric types such as int, 32, it's false for booleans, and it's an empty string for strings. So if I wrote var my name string, declaring a string variable but with no initialization, then it would hold this value here, an empty string. So this is declaring an integer 32 variable with no initialized value. Now, the third way we can declare a variable is a shorthand in Go that you'll see a lot, and it's shorthand for declaring and initializing a variable. So the shorthand for this scenario up here. So what you do is you write the variable name, semicolon equals, and then the initialized value. So here we're creating a Boolean variable called isRequired, and we're initializing it to the value of true. So if we see the comment here, shorthand for declaring and initializing a variable. So this line right here, isRequired semicolon equals true, is equivalent or the same as writing var isRequired equals true. These are the same thing. So, reiterating what I just said, three ways to declare a variable in Go. First being declaring a variable and initializing it. Var my name equals Kevin. Now, you may have noticed that I did not specify explicitly that this variable my name is going to be holding a string. And that's because since I initialized the variable with a string value, Go can infer that this variable my name is going to hold a string. So that's why in the second way of declaring a variable here, where I declare a variable called my age, saying that it's a 32-bit integer data type with no initialized value, I have to specify explicitly that this variable is going to be holding a 32-bit integer because I did not initialize with anything, so Go cannot infer what type of data this variable is going to be holding. And then the final way of declaring a variable was the shorthand I showed right here. This is a shorthand for declaring and initializing a variable. Okay, so now we're going to talk about variable casting. And what is variable casting? Variable casting is simply converting one data type to another data type. So if we had a 32-bit float variable, we want to convert that to a 64-bit float variable, for example. So how do we do this in Go? So we will look at these examples I have written out. So first line here, I'm declaring a integer variable called number1, called number1, and I initialize it with the value of 3. So var, so Go knows that we're declaring a variable here. Number1 is the variable name, and I initialize it with the value of 3. This is an integer variable here. I believe it's 64 bits because I'm using a 64-bit operating system. And then we have a second variable here called var number2 float 32 equals 3.19. Now you may have noticed even though I initialized the variable with 3.19, I still explicitly said that this is a 32-bit float variable, because if I didn't, it would use float 64 by default. It would infer that this is a 64-bit float because I want a 64-bit operating system. And I don't want a 64-bit float, so that's why I explicitly said float 32. Now, here's an issue. We can't add number 1 and number 2 together to get 6.19. Why? Because these are the same variable type. Var number 1 is an integer, and var number 2 is a 32-bit float, so we can't add these. So what you can do is you can convert variable number 1 from an integer into a 32-bit float, and then we can add them together. So here, I'm using the shorthand for declaring initializing a variable. I'm creating a new variable called number1 as float, and I'm going to give it the value of number1, which is here, converted to a 32-bit float. So how do we do that? You just write the data type you want to convert it to, in our case float 32, with parentheses, and then inside the parentheses we pass in the variable we want converted, in our case this integer variable number1. So now, to prove to you actually first that we can't add these two, I'll show you that Go gives us an error when we try to save this file here. So let me comment this out really quick. So if I say, hypothetically right here, if I just want to print number 1 plus number 2, we just do number 1, print line number 1 plus number 2, and we save the file. And as you can see, we get a red squiggly here. Invalid operation. Number 1 plus number 2 mismatch in types, int and float, 32. So Go is already telling us that we can't add these two together because they're not the same data type. So now, after I took our integer variable, number 1, turned it from a integer to a 32-bit float, and assigned it to this new variable here, I can add them and print it. So let's see. So now I'm doing print line of number 1 as float plus number 2. I'll save our file, and then down here I'll cd into the directory that I'm in, where this file is located. Go run variable casting.go, and as you can see, we get our 6.19 printed. So 3 plus 3.19 is 6.19. So since these both are 32-bit floats, we can add them together, and we get no error in this case. Awesome. Okay. So now, a common use case of this is integer division. For example here, if I print 5 divided by 2, we would expect to get 2.5. But as you can see, this won't be the case. We get 2 from this print line here. 5 divided by 2 prints us 2. Why is that? Because since we're dividing two integers, we're going to get an integer back. And integers are whole numbers, so the decimal is truncated, so we do not get 2.5. So what we can do is convert both of these values, both of these integers, into floats. And then when we do our division, we will keep the decimal because floats represent values with decimal points and such. So let's do that example. So here I'm printing number 1 here converted to a 32-bit float, and number 2 here converted to a 32-bit float. Like I mentioned earlier, to convert to a float 32 or to convert to whatever data type we want, we write our data type with parentheses, and then inside the parentheses we pass in the variable value that we want converted. In our case, we want to convert this number 5 from number 1 to a 32-bit float. Similar situation here for 2. Actually, 2 is already a 32-bit float, but it won't really matter. So now if we do this, if we print this, get our 2.5. Because we're dividing two float numbers, we get a float back, and floats hold decimal values. So now we have 2.5. So that's one use case of variable casting here. Okay, so now here's just another quick example of converting from float 32 to float 64. So I create a 32-bit float variable here called myFloat32, and I give it the value of 1995. So if I print that, we should see 1995, right, as expected, because all we're doing is printing this variable here. Now, I convert. Now here, I create a new variable called myFloat64, and I give it the value of myFloat32, but cast it to a 64-bit float. So to do that, I write float64, because that's what I want to convert that to, parentheses, and I pass in the variable myFloat32 with the value of 1995, because I want to convert this variable, this 32-bit float variable, into a 64-bit float variable value. So now, I assign that return value into this variable, and I print it, and as you see, this gets printed. It's a 64-bit float, as you can tell, because there's more decimal places, so it's more accurate. Now that's converting between numerics. So now we're going to go into something a little more sophisticated. What if you want to convert from string to integer and vice versa, integer to string? So here we can't just do the string parentheses and then some int variable here. This would not work. Writing this would not take this integer variable and take that variable and or take that value and turn it into a string, and vice versa. What we will need to use is a function in a package, actually, called strconv, which I imported up here, short for string conversion, I'm assuming. So we're going to import this package, and it has functions inside this package that we will be using to convert from string to integer and integer to string. So let's take a quick look at Go's package documentation for this package. So let's bring up our browser here, and okay, I'm cheating here, I already have it open. Okay, so if we go to the package, if we go to the list of all the packages in Go, and we look for the package we want, okay, so we just scroll through all the packages to find the package we want. It was string conversion strconv, so let's look for that. It's right here. Okay, so next to it is brief description, package, string conversion, implements conversions to and from string representations of basic data types. So that's exactly what we want here. So if we click on it, we'll get everything about this package. This brief overview, and then we get all the functions inside this package, we get all the constants inside this package, and we get examples of how these functions work. And to cut to the chase, our first example will be from changing a string to an integer. So the function we're going to be looking for is called a toy, right here. So if we click on it, it'll give a description of what this function does, give an example of this function, and then it'll give you the function signature here. So we haven't gone over the proper syntax for writing a function yet, so bear with me here. That'll be the next video. So this function here is called a toy, which means ASCII2 to integer. And here we can see that it takes one string variable, which is the string that we want converted to an integer. So it takes one string variable and then returns two values here. It returns an integer, which is our passed-in string converted to an integer, and also returns an error. Now, this error I'll go into a little more detail in a future video, but for now, it pretty much indicates if there was an issue converting our string to an integer or not. So, let's use this function. So I imported up here, and as I mentioned earlier, if you want to import multiple packages, you have to use these parentheses here and put the packages on new lines with no commas. And so I declared two variables here. One's an integer variable called myInt using the shorthand, and my string called not called a string variable called myString with the initialized variable of a string with 5. Now I want to convert this 5, the string 5, into an integer variable 5 so that I can add 7 and 5 together to get 12. So right now I can't add these two together because they're not the same data type. As I showed earlier, we couldn't add a integer and float together because they weren't the same data type. So what I do here is that I call the toy function in the string conversion package. And the nice thing about Visual Studio Code and Go, the Go extension here, is that I can just hover over a toy here. It'll show me exactly what I just showed in the documentation, the description of this function inside the package and the function signature. That it takes one string variable and returns an integer and an error. So, and you can declare multiple variables on a single line, just got separated with a comma. So since this function returns two values, an integer and an error, I'm gonna assign those two return values to these two variables here. So the first thing that's returned here is an integer. So the integer I'm going to put into this variable called string as int, and the error returned here I'm going to put into this variable called err. So here's the shorthand here, call our function, pass in my string variable as an argument, and then take the return values of this function call and assign them to these two variables here. Now, we know if an error occurred if this function returns something. So if it returns something, then we know we got an error. But if it returns nothing or nil, then we know that no error occurred. So we'll go into conditionals and stuff later. But so if there was no error, then we know that the conversion of our string to integer was successful. And then we just print our addition operation here of 7 plus 5. So let's check it out. And yep, we get our 12 printed out. Because my int is 7 plus this variable here, which is 5, it has an integer variable 5 because we converted our string 5 here into an integer 5. So when we add 7 plus 5, we get 12. Okay, now how do we go backwards? How do we go from integer to string? Same way, different function. Now we're looking to use this function called I to A for integer to ASCII 2. And if we look here, we can see that it takes an integer variable, the one that we want converted to a string, and returns a string, which is our integer converted to a string. And this variable only returns one value here. There's no error value returned in this case. So I'm just going to declare one variable here called int string and assign it the value of the return value of this function call. So to call, to call a function inside a package, you write the package name, in our case string conversion, and then use the dot operator, and then the function name inside that package. So string conversion dot I to A, and then I pass in our integer myInt up here to 7. So what we get back is a string with the value 7 in it, and I assign that value to this variable here in string. So what happens now is I'm going to print the concatenation of the two strings, 7 and 5. So this is going to have a string of 7, and I concatenate that to my string, which is a string equal with the value of 5. Concatenation meaning just putting the two strings together as one string. So we have two separate strings here, 7 and 5, and then concatenating them gives us a string of 75. So to show that that works, I will run it. As you can see, our string is here printed as 75. So that's how you convert between numerics, how we can convert from, or not even just numerics, but later we can talk about even bytes and string conversion. But anyway, that's how you cast one variable type to another, and how to convert from integers to strings and string to integers. And so now, to recap this whole video and what we went through, we had a quick crash course on bits and binaries. Um, we looked at all the basic data types in Go. We saw the 3 ways to declare a variable in Go, and we looked at how to cast one variable type to another. And before I let you go, I'm going to quickly talk about the project we are going to do for the next couple of videos. In the next video, we're going to be talking about functions. So this is perfect. So the project we're going to do is going to be creating a package that simulates a deck of playing cards, like poker cards. And in this package, we're going to have 6 functions. A function called newDeck, which creates a new playing card deck. A function called print, which prints the current deck of cards. A function called shuffle, which shuffles our deck of cards. A function called deal, which deals out cards from our deck. A function called save to file, so that we can save our deck to a file on our computer. And a function called new deck from file, where we can retrieve a deck saved in a file and assign it to a deck variable in our code. So we're going to be implementing these 6 functions in the future, and the next video is going to be on functions, so this will be perfect. And so thanks for watching, and I'll see you in the next video.